A photovoltaic cell is made of semiconductor materials that absorb the photons emitted by the sun and generate a flow of electrons. Photons are elementary particles that carry solar radiation at a speed of 300,000 km per second. In the 1920s, Albert Einstein referred to them as grains of light. When the photons strike a semiconductor material like silicon, they release the electrons from its atoms, leaving behind a vacant space. The stray electrons move around randomly looking for another hole to fill, to produce an electric current. However, the electrons need to flow in the same direction. This is achieved using two types of silicon. The silicon layer that is exposed to the sun is doped with atoms of phosphorus, which has one more electron than silicon, while the other side is doped with atoms of boron, which has one less electron. The resulting sandwich works much like a battery. The layer that has surplus electrons becomes the negative terminal, N, and the side that has a deficit of electrons becomes the positive terminal, P. An electric field is created at the junction between the two layers. When the electrons are excited by the photons, they are swept to the N side by an electric field, while the holes drift to the P side. The electrons and holes are directed to the electrical contacts applied to both sides before flowing to the external circuit in the form of electrical energy. This produces direct current. An anti-reflective coating is added to the top of the cell to minimize photon loss due to surface reflection. An element silicon is a semiconductor having 4 valence electrons. Pure silicon crystals are not all that useful electronically. But if you introduce small amounts of other elements into a crystal, the crystal starts to conduct in an interesting way. The process of deliberately introducing other elements into a crystal is called doping. The element introduced by doping is called a dopant. By carefully controlling the doping process and the dopants that are used, silicon crystals can transform into one of 2 distinct types of conductors. An N-type semiconductor is created when the dopant is an element that has 5 electrons in its valence layer. Phosphorus is commonly used for this purpose. The phosphorus atoms join right in the crystal structure of the silicon, each one bonding with 4 adjacent silicon atoms just like a silicon atom would. Because the phosphorus atom has 5 electrons in its valence shell, but only 4 of them are bonded to adjacent atoms, the 5th valence electron is left hanging out with nothing to bond to. The extra valence electrons in the phosphorus atoms start to behave like the single valence electrons in a regular conductor such as copper. They are free to move about. Because this type of semiconductor has extra electrons, it's called an N-type semiconductor. A P-type semiconductor is created when the dopant, such as boron, has only 3 electrons in the valence shell. When a small amount is incorporated into the crystal, the atom is able to bond with 4 silicon atoms, but since it has only 3 electrons to offer, a hole is created. The hole behaves like a positive charge, so semiconductors doped in this way are called P-type semiconductors.
Photovoltaics, a hard word to say, but it's made of 2 simpler words, photo for light and voltaic, which has come to be associated with electricity because of Alessandro Volta, who invented the battery. So photovoltaic literally means light to electricity. And nowadays, solar cells are roughly 22% efficient at converting light to electricity. And there are some solar cells for spacecraft that are probably above 25% efficient. It is being improved. And even at the efficiency we have today, there's absolutely no problem with using it to power everything. In its basic form, you take 2 materials or 1 material with different impurities in it. With a silicon solar cell, you have silicon. You can make it into a crystalline material. So you think of it as a lattice of atoms in there. Now you put some impurities in there. One kind of impurity, boron, will lead to a deficit of electrons in your lattice, which means that that material will now be positively charged. And phosphorus will lead to extra electrons in your lattice. So now your material will be negatively charged. So normally materials are neutral. They don't have any electric charge to them, but you can set it up so that they do. And at the interface between those 2 areas of your silicon, You got plus one side, minus on the other. Now you have a neutral region in there, and you also have an electric field because you got pluses on one side, minuses on another. You don't have to have any external thing to make that electric field. The electric field is a virtue of the material alone. When light hits that material and jostles an electron loose, an electron is a negatively charged particle, and an electric field is there, the electron feels a force. Force leads to motion. So you've created a current. That is a simple concept, and yet think about it, our civilization is built upon that idea of the semiconductor device. And the solar cell is the simplest one.